Okay, good afternoon, everyone. So we're going to go over graphing a function with asymptotes. The example is to graph this function, f(x) equals x plus 1 over x. So the derivative of this function is, so you should all see by now that this function is the same as x plus x to the negative 1. Its derivative is 1 minus x to the negative 2. If we set this equal to 0, we'll get the critical numbers for this function. So this 1 minus x to the negative 2, that's the same as, so this equation is the same as 1 minus 1 over x squared. 0, it's the same as 1 over x squared, which equals 1. It's the same as x being plus or minus 1. So these are the two critical numbers. Critical numbers are negative 1 and positive 1. Okay. Okay, so the critical numbers are negative 1 and positive 1. F prime, so as we saw before, when we break it, we can use the critical numbers to divide up the real number line into subintervals. We divide up this real number line into subintervals, negative infinity to negative 1, negative 1 to positive 1, and positive 1 to positive infinity. We look at f prime, right? What is f prime? Well, f prime, we're going to plug in, say, our favorite number that's less than negative 1, say negative 2, to the real number line. We plug it back in, we get 1 minus negative 2 in parentheses to the negative second power. So f prime is, so notice, if you plug in negative 2, what do we get? We get, this thing squared is going to be 4. 1 minus 1 over 4. It's 1 minus a fourth, which is 3/4. That's a positive number. Now, if we pick a number, we forgot one critical number, that's 0. Critical number 0, that's because f prime doesn't exist. So we also need to divide up f prime negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. Between negative 1 and 1, if we just pick, say, our favorite number, let's say a half. Well, in that case, when you plug in a half here, what do we get? That's the same as negative 3. F prime of 1/2 is negative 3. So f prime is negative. Minus a half. But notice we're squaring this, so it doesn't matter. It'll be the same thing. Negative a half, positive a half, doesn't matter. It's also negative between 0 and positive 1. When x is larger than 1, again, let's say we just plugged in, say, 2. Again, it'd be 1 minus 1/4, which is 3/4. That's positive. So we've seen this before. There's nothing new here. We can conclude that f, the original function, is increasing on negative infinity to negative 1 and f is decreasing on -1 to 0, union 0 to 1. So these are two pieces of information we're going to include in the graph. So far, a prototype for a graph is going to look like the following. -1, 0, 1. So let's see, it's increasing here. And then it starts decreasing. Okay, we don't know what happens at 0, but we do know it has to start decreasing from somewhere here, and then start increasing again at 1. Actually, 1, what is the value of the function? The value of the function is 2, so it really should be up here. So it has to go. Okay. We'll look at this a little more later. But that's it for now. So actually, we'll see later on that the function actually has a, what's called a vertical asymptote at x equal to 0, and also a slant asymptote at y is equal to x. Okay, now we are going to look a little more. To get the concavity, we've seen this before, the second derivative, it is what? It is 2 times x to the -3, which is the same as 2 over x cubed. So here, the only place where the function could change concavity is at 0. And actually, we can just test that really easily. Okay, here's 0, divides our number line into 2 subintervals. Here's f double prime. When x is less than 0, f double prime is what? It is negative. When f double prime is when x is larger than 0, f double prime is positive. Just plug in and say -1, positive 1. -1 cubed is -1. 2 over -1 is -2. 2 over +1 is +2. Okay, so that actually confirms what we have. It looks like a hill when x is less than 0, and it looks like a smile or a valley when x is larger than 0. Okay. So as we can see, it has a local max, x equal to 1, local min at x equal to -1, local min at x equal to +1. Okay. Second derivative is, so second derivative got us intervals concavity, first derivative got us intervals of increase decrease. The second step is to find the asymptotes. So there is here, you can actually see here from this graph, really, how is the function going to maintain decreasing, right? Decreasing to what? Well, it can really only decrease, it could decrease to a value, but how it's going to be decreasing concave down? The only way that can really happen is if we're to have a vertical asymptote at x equal to 0. So, and you can verify this, right? When you plug in, if you look at the original function, when you plug in x equal to 0, this becomes 0, this is 1 over 0. Actually, if you notice, limit x goes to 0 from the left of f of x, it ends up being the same, because this first term vanishes, as limit x goes to 0 from the left of 1 over x, which is equal to negative infinity. And likewise, so that's why it's going down here to minus infinity. We can also say limit x goes to 0 from the right of 1 over x is what? I'm sorry, of f of x. X goes to 0 from the right of 1 over x, which is positive infinity. Okay? So that confirms that we have a vertical asymptote at x equals 0. But the other thing, what about this thing here? This here. This is also actually an asymptote. Why is it an asymptote? It's an asymptote because when we set y is equal to x, that's an asymptote. So because when x goes to infinity, this term vanishes. What are we left with? We're left with y equal to x. It's called a slant asymptote. So really, the only new thing here is the following. The function has a vertical asymptote at x equal to 0. That's as x approaches positive. And again, the reason for that is if we look at this function, right? What happens? X plus 1 over x. This is when x is large, this is very small. So this is approximately equal to x for large x values. And also, it's actually approximately, for large x values, also small x values, that is, x values that are large in absolute value, but tend to minus infinity. So the function also is coming up from this actually always ends 0, so actually ends up coming up -1, it is at -2. That's what it ends up looking like. Okay. So notice actually just knowing what the shape of the slant asymptote was allowed us to restrict some values. But what's more important than that is knowing the slant asymptote and also the shape. And so we're just adding one piece of information here. That is asymptotes in addition to shape.